This theorem establishes a connection between the two branches of calculus, taking derivatives and taking integrals. It's going to link the two. The concept of differentiating a function, which remember is calculating the slope of a curve or rate of change at a particular point on a curve, on a function. And the concept of integrating a function, calculating the area under its graph to the x-axis, or the cumulative effect of small contributions along the way. And we did that. Did we do the one where the water was dripping out, where we had the table and we had to add up all the pieces? Yeah. So here we go. Roughly speaking, the two operations can actually be thought of as inverses of each other. Derivatives arose from the tangent problem. How can I get the slope of a curve by using the tangent but making the tangent get closer and closer and closer so that the difference between the 2 points is basically 0. And the integral calculus arose from finding the area under a graph to the x-axis. Seem to be completely unrelated, right? Let's find the area under a curve to the x-axis. Let's find the slope of a point on a curve. Those are the two areas of calculus we're concerned with. What FTC says, fundamental theorem of calculus, that differentiation and integration are in fact inverses of each other. It will allow us to compute areas and integrals very easily without having to compute them as the limit of sums of whatever shapes we're using. Rectangles, we use some triangles, we use part of a circle, trapezoids, and we don't have to do that. It's widely regarded as one of the most significant intellectual achievements in human history. Yes. It isn't just a math rule, it's the bridge that connects two seemingly unrelated worlds. This is what makes us highly intelligent species. Before this discovery, geometry, the study of shapes, and algebra, the study of equations, were separate entities. And you may have thought they were too, because in high school, we kind of treat them separately. The fundamental theorem of calculus, it has simplified the impossible, and it created the language of modern science. Without that, I would argue we'd still be in dark ages. Whoops. This is on canvas. Its brilliance lies in its unification of two seemingly distinct areas of mathematics. It not only provides a theoretical foundation for calculus, but also offers practical tools for solving countless problems that exist in science, engineering, and things we haven't even thought of yet. Okay. So if g is defined as the integral of f, then g turns out to be the antiderivative of f. G is the integral of f, then g turns out to be the antiderivative of f. Let's look at our very first example, number 1, okay? And then we'll come back. Okay, so we have this. F is a function whose graph is shown below. So g of x is the integral of f. Okay, I got it in terms of t, which might be time. So let's find the values of g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. And then we can maybe sketch a graph of g. Let's figure this out. So g of 0. G of 0. According to this, that means I want to take the integral from 0 to 0 of this function. We're going to rely on anybody. I mean, it's on your sheet, but try to highlight what it looks like. there it is, highlighted there. F of t. Okay. Remember the integral is the net area under the curve, net area under the curve, between the curve and the x-axis. So I'm going from 0 to 0. What do you think that is? Is 0. Okay, we got that. Then I want to do g of 1. According to that, I'm going to do 0 to 1, f of t, dt. Let's see what that one is. Oh, that's this right here. Going from 0 to 1, and integral is the area under the curve between 0 and 1. Does anybody have an idea what that is?
2.
Not 2.
Oh. 1. Right.
Yeah, 1/2 of 2. Because I'm going to have 1/2 base times height, because it's a triangle. And the base is 1. 1/2 base times height. Then it says let's do g of 2. This is what we've sort of been doing. And according to this, let's go from 0 to 2, plug it in, f of t. We don't have a function to plug it into, but remember, I said I love when they give you graphs and tables. It's so much easier. Let's see, now I need to figure out the area from 0 to 2. Anybody have any idea what that is? 3. Aren't we just taking this area and adding this new area to it? So I'm going to have 1 plus the new area equals 3. Okay, now we got to do g of 3, sorry, which is the integral from 0 to 3. This function that we graphed over here. So I've got this and this and, we may have to kind of estimate that area, right? What do we think this area is right here that we're adding? We probably have at least 1 full square and a little more. So 3 plus 1 point, I said 1.3. I don't know. You can look at yours and see. Looks like I had that little piece and then maybe a little bit less than half left. I thought we had a little bit less than half left over, so I'm going to say about. So that's going to add up. So far we've got this and this, and now we just added this. And now we're going to go g of 4, which is the integral from 0 to 4 of this function that we graphed. And I'm going to say that's about, well, it's going to be this, and then something else. But remember, this is net area, right?
I would say 3 again.
Yeah, maybe we took away about a third, so we can do the last one. Oh, wait a minute, you said about 3?
Mm-hmm.
Yeah. The last one and subtract. Wait a minute, am I doing that right? 1.3. So about 3 again.